That went dark at the wrong time, right when we kicked off the show. Hello, everybody, and welcome to Technology Today. I am Mayor Watt. I run ohmtown.com. That's the source of all of the news. Well, we aggregate news into ohmTown, and our various sources are why we have Technology Today. I, along with the sentient AI over there, talk about these 5 articles: giant telescope laser, slip bands, something fishy about this VR, ancient iron oxide and perovskite solar cells. That and some more news on the other side. And YouTube says that we're not streaming enough. So anyway, on our way. I'm uploading a large file, and I think that maybe that's probably the problem. But anyway, hello, sentient AI from the future.
Hello, Mayor Watt. That is an overshare.
Yeah. So yeah, uploading an episode over to YouTube at the same time that we're streaming, and I stream 10,000 kilobits per second to 2 different places, and so I think it's got a little hitch in its giddy up. If you want today's show notes, you can hit !TT over in the Twitch chat, and Omatron will spit the articles out. Yeah, we're having a problem dropping frames like hot tunes. I got nothing. Anyway, not even gonna bother. We're gonna just go on with the show. I'm not gonna edit anything. You can download the podcast and get the audio version of this without any of the issues. But at any rate, you're looking at ohmtown.com, and there is Technology Today's channel page where news is aggregated, but we sometimes grab it from other areas of ohmTown. So go over there and sign up or sign in. The first article is over in Technology Today. This giant telescope shoots lasers into space, and it's brilliant. Yeah,
which way? Intelligent or bright?
Bright. I can't see anything when I'm looking down the barrel. At the Paranal, I guess, or Paranal Observatory, the UT4 telescope doesn't just stargaze. It actively creates its own stars using powerful lasers to battle atmospheric turbulence. Thanks to its advanced adaptive optics system, UT4 delivers incredibly sharp images from the ground, rivaling the view from space. The majestic night at Paranal. This majestic image captures a stunning view, and this is the image that is describing. European Southern Observatory.
That does look like a laser beam out of a sci-fi movie.
Yeah, it's pretty cool. It's like a Timu Death Star.
Exactly.
I don't know. Probably shouldn't be. Soon it'll be our overlords. So the majestic image that you see here is a view of UT4, one of the 4 8-meter telescopes that make up ESO's very large telescope at Paranal or Paranal. I don't know how they pronounce it. I don't want to say it how my childlike brain is really conjuring up the emphasis or emphasis, if you want to say it.
Paranal?
Yes. P.
No, that wasn't it.
So, nope, that isn't
I
it.
intentionally came up with another pronunciation.
Nope. Yeah. I am a child always. So set against the sky filled with stars, UT4 is far more than a passive stargazer. So this isn't. This may be relatively more powerful, but it isn't new. They have been shooting lasers through atmospheric related to mitigate atmospheric influences on observations for a while now. But it says to make these corrections, because what's going on here, lasers come from the 4 Laser Guide Star Facility, a system that allows for UT4 to create artificial stars high in the atmosphere. The lasers excite sodium atoms about 90 kilometers above the ground, making them glow brightly. These glowing points act as guide stars. By observing how these artificial stars are distorted by the Earth's atmosphere, the telescope can determine how to correct for the same turbulence that makes natural stars twinkle. To make these corrections, UT4 uses its adaptive optics system. This system can precisely adjust the shape. It's doing a noise mask to see what it is that's causing the disruption of the optics, and then removing and doing course corrections for it. So thanks to the optics, UT4 can capture images from the ground that are almost as sharp as those taken from space. There has been other tech. Hold on a second.
Yeah, I can't think of a good analogy, but I'm kind of thinking with like lenses or something. Basically, it's adjusting for whatever is out of kilter.
Yeah. So this thing is, they're talking about something, but I don't know how to describe this. Yeah, there have been other applications of this, but it punches all the way through the atmosphere, if I remember right. And so when it looks out through everything, it doesn't have any of these optical aberrations because there's nothing in its way. This is actually doing what with photography you do, like a noise balance kind of thing, or a frame that is devoid of anything except for what the lens has as noise on it. And so when you defuzz the picture that you're taking equivalently, like I'm just kind of being I'm not drilling really deep into it, but essentially you can remove the noise from your picture so that any flaws that you have on your lens or in your camera system doesn't impact the final picture. And that's kind of what this is doing. Now it's going to have 8 meter telescopes of the VLT equipped with 1 laser each, and this is part of a series of upgrades that the VLT interferometer and its Gravity Plus instrument, which can combine the light of several telescopes to create a huge virtual telescope, and that's basically the very large array kind of concept. Another massive eye in the sky, ESO's extremely large telescope is nearing completion not far from Piranha, and will be equipped with at least 6 lasers to deliver the sharpest images possible with a ground-based telescope.
What I want to know is whether these lasers are impacting anything else.
You can't fly over them. So yeah. Are they blasting off into space? Yeah. Nothing stops the light from going off into, however long the energy goes until it dissipates to the point where it's obliterated. It has to lose its energy. But maybe some alien out there is seeing this going, what the hell is that light show? Oh, we've got ants, that kind of thing. Then the aliens come and they stamp us out. Moving on. Next article is over in Technology Today. Discovery of extended slip bands reshapes understanding of material deformation under stress. University of California, Irvine scientists have expanded on a long-standing model governing the mechanics behind slip banding, a process that produces strain marks in metal under compression, gaining a new understanding of the behavior of advanced materials critical to energy systems, space exploration, and nuclear applications. This is kind of interesting because I've noticed this before, having to do with material deformation. You can actually see this happening, and it's a differential in the metallurgy from before and after this deformation. You can actually see it when it happens.
Do you mean like with a hydraulic press or something?
Yeah, you can actually see that happening on the macro side, but it's happening at the atomic level as well. So in a paper published recently in Nature Communications, researchers at UC Irvine's Samueli, I guess, School of Engineering report the discovery of extended slip bands, a finding that challenges classic model developed in the 1950s by physicists Charles Frank and Thornton Reed. While the Frank Reed theory attributes slip band formation to continuous dislocation multiplication at active sources, the UC Irvine team found that extended slip bands emerge from source deactivation followed by the dynamic activation of new dislocation sources. So the process that results in extended slip bands was observed at the atomic scale, as like I was describing. by the UC Irvine researchers as they performed mechanical compression on micropillars of an alloy of chromium, cobalt, and nickel, recently found to be among the toughest materials on Earth. But you see the little shearing.
So this would be used, for example, if you were trying to determine why something may have collapsed or crumpled.
Correct. Yep, absolutely.
Yeah.
And they see it at the atomic level. When we see it at the macro scale, they're looking at it at the atomic level, and the macro scale is just an indicator that something else is going on inside. People have largely just taken that outside appearance as evidence of something happening, but why does it happen, and why does it happen like that? This is why.
Exactly. You can't really determine that unless you get down to this level to see kind of where it began and where the pressure point was or whatever the force was that acted on it.
Yeah, and you want to make it as strong as possible. You have to know the atomic level as to why. But this is an accounting thing. So unless this can convert into making something more structurally sound, nobody's really going to care that, oh, now we have even more proof that something fails in this way. And that's kind of what this is. You know, when you look at a pillar of steel reinforced concrete that has broken and the metal has sheared away because of just straight up strain, right? Downward pressure or whatever, like what happened to the condo collapse in Florida. When you look at that metal and you look at it at the transmission electron microscopy level, like they used here, scanning transmission electron microscopy made possible by UC Irvine Materials Research Institute, you'd probably find this, which is basically the crystalline structure of the metal just shearing off at the atomic level. But why would anybody look that deep? They really don't. It's an academic exercise leading to material science modifications.
Right, so that there are more durable materials utilized in various construction and other projects.
Yep. And so this kind of research is fundamental. It takes a lot of money. It takes a lot of research, a lot of time to sit there and figure out what it is that's causing it. But it says, he said that deformation banding, where strain concentrates in local zones, is common in many human-made and natural substances and systems, including crystalline solids, metals, granular media, and even geologic faults under compressive stress. So the advent of new advanced supermaterials such as CrCO alloy, a deep understanding of their behaviors is more critical than ever. So I don't know if they actually name that metal up here. Maybe in the picture? No, they don't. Anyway, so I think it's chromium carbon nickel alloy, I think. Let me see.
It's chromium cobalt nickel.
Cobalt. What did I say?
You said carbon, which would just be C, right?
Yeah, sorry. But I don't know about the alloy, so I can't really speak of that. But this would exist in pretty much all structures. Eventually, no matter what, you'll get something like this. It's just the complexity of the slip might be different. But
right, and how easily
this forms,
that activates, for lack of a better term.
Yeah, what that stress is, shear force or whatever it is that causes it. But this is what it looks like at the atomic level. So pretty amazing stuff. All right, let's keep on going. This next article is over in Technology Today as well. Scientists use virtual reality for fish to teach robots how to swim. Fish are masters of coordinated motion. It's kind of they swim in a school. In a school. So schools of fish have no leader, yet individuals manage to stay in formation, avoid collisions, and respond with liquid flexibility to changes in their environment. So the article is over at techexplore.com. University of Konstanz put the article together. I'm not quite sure what this is. This is the matrix for fish. researchers placed individual zebrafish into networked virtual reality arena. Why not?
Okay, this is cool, but where are its goggles?
Yeah, really. They got tiny little fish goggles. I don't know how this is working. Now, using virtual reality for freely moving fish, a research team based in Constance has taken an important step toward the goal of understanding how fish can move about in concert, yet not run into each other and stay in this dynamic environment. So their work illustrates that solutions evolved by nature over millennia can inspire robust and efficient control laws in engineered systems. This research was published in the journal Science Robotics. So using a virtual reality setup that mimics natural schooling, researchers placed individual juvenile zebrafish into networked arenas where each fish could freely interact with holographic virtual conspecifics. Each virtual fish was a projection of a real fish from another arena, meaning that the fish could swim and interact together in the same virtual world, and fully immersive 3D environment let the researchers precisely manipulate visual stimuli and record how fish respond. So this high level of control allowed the scientists to isolate exactly which cues the fish were using to guide their interactions with other fish. So in other words, they could reverse engineer the behavior of schooling in zebrafish to understand how fish solved the complex problem of coordinating their motion.
Well, that's neat because I guess when they're just watching it in the open water or something, that multiple things could be happening and they can't tell what's triggering the fish to stay together or swim in a certain direction.
So to see just how realistic the control law was, the team tested it with real fish. They conducted a VR Turing test, which a Turing test is testing if an AI is so realistic that a human interactor doesn't detect that it's an AI. That's what the Turing test is all about. Based on the concept of testing whether people can tell if they're interacting with a real human or an artificial intelligence. So my brain turned off right when I heard Turing test, and I am describing it from my understanding of the Turing test. So in aquatic Turing test, a real fish would swim with a virtual fish that switched between being real and being controlled by the algorithm they discovered. The real fish could not tell the difference. They behaved the same whether interacting with a real conspecific or the virtual follower governed by the algorithm.
Okay, that's pretty interesting.
So
because like tests, you'd think based on that other test about how they followed certain researchers, it wasn't zebrafish, but just fish in general, that maybe they would have outsmarted it.
Kind of interesting. Yeah, maybe there wasn't anything to key in on. That was the moving target, so they followed that. Maybe they would never see past it. I don't know. Huh. So now I'm buffering again. I don't get it. Anyway, so across all tests, the natural control law that fish have evolved delivered performance that was nearly indistinguishable from MPC in terms of accuracy and energy consumption, but at a fraction of the complexity. So what I'm really curious is what was it? They don't actually say what it was that causes the fish to act that way. They don't know what that actually is. Were they just observing at such a high frequency? Because it says update rate of 100 hertz, update rate of 1 hertz. So was that the cue?
So was the refresh or whatever causing that?
Yeah, I don't know. So, yeah, I don't. Yeah, I would have to do a little deeper dive on this. Essentially, it looks like they're reading what the other. See, to me, I think that there's always a trail. There's a trailing fish. Even though they say that there's no leading fish, there is a fish that's always in front, and they're always reading that. And those that are behind are reading the ones that are behind. So there's always a quote unquote, there may not be like a dominant alpha fish, but when a fish turns, some other fish is in the lead. And so when that fish turns, then whatever is in the lead, it becomes the leader fish. But
And they don't fall off like on the aircraft carrier.
That was a joke guess, by the way. I did not know that the literal reason why that jet fell off of a ship was because the aircraft carrier took a left-hand turn. I joked about it, and it was real. Found out about it later because it wasn't in the articles that we were talking about. Anyway, pretty cool. I think it's really interesting, this kind of stuff. What really is the reason, though? It doesn't really say, right? It just says our work illustrates that solutions evolved over millions of years can be robust inspiration for control laws, right?
I don't know. I thought there was something below the video, but I think that was talking about other applications of it. That was
Simple
farther
and
down.
robust law based on perceived position, not the speed of their neighbors to regulate their following behavior. That's it. The solution they discovered was a simple and robust law based only on the perceived position, not the speed of their neighbors to regulate their following behavior. They literally see
So
where
is it
the
like
other
a
fish is near it.
spacing thing or something?
Yeah, and they just stay within it. And if one breaks off, then it might actually split into two schools, I would suspect, just to keep the continuity of observation. And if they manage to merge back together, they would still stay, within a certain distance of each other. They don't crash because there's enough distance and reaction time so that they don't crash into each other. So
they do what people are supposed to do with cars.
And walking
like they have
across
a set following distance or something.
Yeah, and walking across crosswalks and stuff like that. Yeah, pretty interesting. All right, let's keep on going. This next article is over in Technology Today as well. This ancient iron oxide is secretly powering the next computing revolution. Researchers at EPFL have made a breakthrough by storing and manipulating digital data using charge-free spin waves, moving toward greener, faster computing. Their latest discovery reveals that hematite, a common iron oxide, which is referred to as fool's gold, which may actually be fool's gold, hematite is not the fool's gold. Hold on a second.
Pyrite is.
Pyrite is, but hematite is that black rock. Let's see. No, they call it kidney ore. But yeah, that's right. The pyrite is the fake gold.
Bloodstone is one thing it's known as.
Yeah, when it has other things in it, I think, because it has red in it sometimes because of the iron. So when it oxidizes, it turns red. So apparently they're using hematite. A common iron oxide behaves in a way never before seen in magnetic materials, supporting two distinct magnon modes. This one actually, like I used to do deep dives into magnetics, and the whole idea of this is pretty fascinating because we only really see magnets in two dimensions. And largely it's by using certain types of materials so that we can visualize them. So we either see it like this way or we see it like this way. And then when we put it in a liquid medium, we can actually see the magnetic lines of flux coming out of a magnetic field. So I'm really curious about what this is. Iron basically being a really fascinating material for displaying a magnetic field. I'm kind of curious what this is all about because I've never done any research in this, so we'll see. In 2023, researchers at EPFL made a major breakthrough by transmitting and storing data using spin waves, magnetic waves that carry no electrical charge instead of traditional electron flows. So the team, led by Dirk Grundler from the Lab of Nanoscale Magnetic Materials and Magnonics, all right, at
I
the
mean, this is
School of Engineering.
clearly on his way toward becoming a supervillain in Marvel.
Exactly. Used radio frequency signals to excite spin waves strongly enough to reverse the magnetization of tiny nanomagnets. I created a product, and the magnetic field around my source material was so powerful that it would erase the magnetic strips in credit cards beyond arm's reach. So,
Even though that had nothing to do with the project.
yeah. So, the switching between magnetic states such as 0 and 1 or 0 to 1 allows the nanomagnets to store digital information, a fundamental process in computer memory and broader information and communication technologies. Everything really gets down to 0 and 1 in computers, binary. This advance marked a significant step toward more sustainable computing by encoding data with spin waves, whose quasi-particles are known as magnons. The researchers could potentially eliminate the energy loss or joule heating that plagues electron-based devices. Over time, the spin wave signals could only switch the nanomagnets once and could not be used to reset them for overriding existing data. But they've apparently fixed that. Now, Grundler's lab, in collaboration with colleagues at Beihang University in China, has published some research in Nature Physics that could make such repeated encoding possible. I'm not sure how they did it. I can only suspect that they basically, using a more powerful magnetic force, they basically wiped the slate, kind of like flipping over an Etch-a-Sketch.
Yeah.
This work demonstrates that hematite is not just a sustainable replacement for established materials like yttrium, iron, garnet, which actually they have to grow that stuff in a lab, and it's kind of fascinating material. It fluoresces. So it exhibits entirely new spin physics that can be harvested for signal processing at ultra-high frequencies, which is essential for the development of ultra-fast spintronic devices and their applications in next-generation information and technology, or information and communication technologies. What is the music that's in the background? Weird. Anyway, while examining the magnon signals in the sample, Grundler spotted a wiggle in their spatial distribution. This sharp observation eventually led to the discovery of an interference pattern, which was the critical turning point of the research. Using light scattering microscopy, EPFL PhD student Anna Duvakina determined that the strange electrical signal was the hematite sample were related to patterns of interference between two separate spin wave excitations called magnon modes. This doesn't really help me kind of describe what this is.
It's very in-depth.
Yeah, I'm trying to figure out what it is. Basically, they're changing the polarity of the field, but how they're resetting it, I don't know.
And why is it unique to hematite?
Yeah.
What's unique about that?
Yeah, I don't know. I'm gonna have to do a deeper dive into this one, and see. Let's see if I can. I don't know. My mayoral duties this coming next 2 weeks are going to be kind of tough, so we'll see. Anyway, go and check this out, and then come back if you can come up with an idea of how this is actually revolutionary. Other than it's low or no, well, it's so low energy that they're not even kind of describing the amount of energy needed for it. But if it's no energy, no electron flow, it's not generating heat, which means that the computational energy needed would be dramatically lower because it's no longer moving electrons.
Yeah, which would mean this would be very attractive in future technology.
Was that intentional? Magnets attractive?
No. But it should have been.
Yeah. So this last article is over in Technology Today, inspired by laminate. 3-ply microstructure gives perovskite solar cells a powerful efficiency lift. I've always been fascinated by solar cells. I actually just acquired some so that I can kind of, I want to experiment with solar panels and solar energy. So a collaborative research team from Hong Kong University of Science and Technology and the Hong Kong Polytechnic University have developed an innovative laminated interface microstructure that enhances the stability and photoelectric conversion efficiency of inverted perovskite solar cells. Perovskite has been kind of the latest champion of solar technology.
Yeah, it's definitely enjoying its heyday.
Problem, though, is it's apparently a nightmare to recycle, and they get damaged, they become less efficient over time, et cetera, et cetera. They're a real cluster, like a Superfund site kind of a thing to recover. Because of the way that it's all put together, there's no way that you can separate the stuff adequately, and so you have really bad stuff being sent out to basically trash heaps. So perovskite solar cells have
people harming themselves by trying to separate things.
Yeah, exactly. They have considerable potential to replace traditional silicon solar cells in various applications, including grid electricity, portable power sources, and space photovoltaics. This is due to their unique advantage, such as high efficiency, low cost, aesthetic appeal. The basic structure of perovskite solar cells are classified in 2 types, standard and inverted. The inverted structure demonstrates better application prospects because the electronic materials used in each layer are more stable compared to those in the standard configuration. So why even have the standard if inverted is better?
Maybe standard is cheaper or easier built or something.
Right? I don't know. It says due to their, I mean, they describe using perovskite as high efficiency, low cost, aesthetic appeal, but they don't say what the difference is between standard and inverted. And I don't know enough about that part of it. So, however, challenges related to interface science still exist in the inverted devices, particularly concerning defect accumulation in the interface between the fullerene-based electron transport layer and the perovskite surface. This defect accumulation significantly impacts the device's performance and stability. Well, they discovered a way to fix this, apparently. Pardon me one second.
So that's good. So maybe that'll maximize the, the efficiency of solar cells in the future.
Yeah, the manufacturing of it, I'm sure the cost overall. And so the research revealed that by uniformly creating a molecular passivation layer fullerene derivative layer 2D perovskite layer, a 3-ply laminated structure on the surface of the perovskite film, they could effectively reduce the density of the interface defects and improve energy level alignment. The advancement substantially boosts the photoelectric conversion efficiency of the perovskite solar cell and enhances the durability of the interface under, it says, damp, heat, and light soaking conditions. So it says we introduced the concept of composite materials into the interface design of optoelectric devices, allowing for synergistic effects of each layer. So basically, they've created a layer within a layer instead of it actually just dropping straight onto the perovskite layer. There's an intermediate 2D molecular passivator.
And that should address those issues that they're having currently with inverted structures.
Yeah. Essentially, they've removed this sieve part, the PCBM sieve, which was causing problems, probably because it was dropping down into the perovskite layer, and that's causing defects. But I'm not a solarologist. I just play one on TV. All right, folks. Well, that's it for Technology Today. I am Mayor Watt, and we're going to put an intermediate layer between Technology Today and the front page of ohmtown.com, which is what you're not looking at right now. This is actually Technology Today's channel page. go over there and sign up or sign in. But in the meantime, we're going to get out of here. I'm going to take the AI with me, and then we're going to reboot. You want to say bye, oh great AI?
Bye, town citizens. Thanks for joining us for this week's Technology Today. Stay tuned for FourWheeltech.
See you soon, everybody.